My name is Xavier Besseron. I'm a research associate at the University of Luxembourg. So let's say compared to Fosdem, just heard about the administrator, one of the administrators of the cluster. I'm more on the user side, so the guy who's complaining all the time. So yeah, this talk is about like automated testing of installed software, but actually it's only focusing on MPI stacks as one of the installed software and one of the key installed software on the HPC cluster. So first a bit of context and motivation. So on HPC clusters, on the HPC side, there is a large variety of software that are required by all the users. One example we saw, which is HPC BIOS, which defines all the set of software that the user might want to have to perform some kind of task. And of course, like just the work to install, maintain, and updates, and is a really huge work. So, of course, and hopefully for those admin guys, there are a lot of tools, or not a lot, but a few tools to help to manage the software on the HPC cluster. So, for example, there is EasyBuild, which helps to build, install, but also reinstall in a reproducible way all the software you might need in your cluster. And also, there is module environment that will help you to switch from one flavor of a software to another. So flavor is more like a version of the software, but also it depends on the version of the software plus the dependent library that it's using. So just quickly, I counted the number of easy config files in EasyBuild. Might not be accurate, but I counted like more than 2,000 that you can just build right away using EasyBuild. And yes. So that's the context of HPC cluster right now. So one example at the University of Luxembourg, a few statistics about the software installed there. So currently we have two clusters, or no? We have two clusters using build, and they provide about more than 1,000 modules, each of them. So many of them are just duplicated versions, like different versions, built with different toolchain, etc. So I counted like 376 different software of libraries. But for example, we have 25 installed versions of Xavier, which is a lot, just for Xavier. For example, we have 15 different flavors of GCC. And some of the software like Romax, OpenBlast, Scalapack, 10 different flavors, and yeah, that's it. So what we notice is that we have, thanks to tools like EasyBuild that help us to build a lot of software very easily, at the end we have an explosion of the available software. So still at the University of the Cluster of the University of Luxembourg, now let's just focus about on the MPI stack. So we have the four big major families of MPI installed at the University of Luxembourg. So we have OpenMPI, MPH2, MPH, and Intel MPI. So here I listed the versions that are provided on our cluster. So for OpenMPI we have 5 different versions installed. MPH2 we have 3 of them, MPH we have 3 of them, and Intel MPI we have 8 of them. And for some versions, actually they are built with different toolchain. So we don't have all the combination of all the version and all the toolchain installed, but at the end we end up having 31 modules that provide MPI on our cluster, which is a lot, in my opinion. And what is the problem with this? We have a lot of MPIs provided, so that's good, we can choose. But actually, the problem to me as a user is that some of them are not working out of the box. So why they are not working out of the box? So that what I wanted to find out, and why also I want to do this, because I just want to complain to my sysadmin and yeah, spend my time complaining. And also at the end we can fix it. Yes. So basically, when you want to test an MPI stack, what you are going to do, like I'm just a simple user, and so I'm just going to run the simple stuff. So I'm going to test the important like binaries or executable you expect from an MPI. So for example, it can be MPI CC and MPI run. Then you just want to compile a simple hello world program with MPI CC. And also you want to run it. So on 2 nodes to test also the network if it's working properly. The third step you might want to go for is testing some micro benchmarks. So, okay, it's some more additional step, but it's not much more complicated. And for example, we can take the OSU micro benchmark and test run the bandwidth test and the latency test. Probably what you want to do after this is check that the performance you have is actually the performance you expect from your cluster regarding your interconnect and everything. So some later tests we can imagine is running HPL or some more, let's say, some other benchmark or some other software that make a user use of MPI. But yes, that's the beginning. So it's easy to test one MPI stack, yes. But if we want to test many MPI stacks, for example, the 31 we have at the university. So yeah, just take what I wrote before and do it again and again and again. Every time there is a new MPI stack. Yes, but let's do a little bit better. So you put all the kind of tests you want in some script or in separate test script. Then you want a list of the MPI stacks you have installed. You want to run the script for all of them, but you also want to collect the data, the result for all the different tests. And then you want to present them in a synthetic way, and you want to repeat this from time to time, and also repeat this when a new MPI stack is getting installed. So that's why I incrementally, like this, I ended up having, let's say, this, I call it Lattice framework, which just provide a simple way to test my MPI stack on my on the cluster of the University of Luxembourg. So yes, so what this framework is about. So I'm a kind of lazy guy, so I don't want to do like a lot of stuff that has been invented before. So I base my work on some existing testing framework that I know how to use. So this is CMake and CDash. So actually, one of the tools I use is CTest. It's a tool distributed together with CMake, and so it's a tool to run tests. It's meant to automate the tests and run them like properly, and also collect the result and submit them to a CDash or Dart compatible dashboard system. The second tool I use is CDash, which is this time is a web-based server and interface that will just collect and gather all the results submitted by CTest and present them in a nice way in a web browser, aggregate the result, and yeah. One of the nice features of CDash is I can ask him to spam the sysadmin when there is a problem with one of the MPI stacks. And also it's using like some kind of other tools, some kind of like shared scripting for plotting. NumDiff, which is a nice tool that allows to compare like text file, but from the numerical point of view, and some control to automate other things. So the current status of this testing framework is, so right now it's only focusing on MPI testing, so no other software. This can come in the future. Also, it's only focusing on the general behavior of MPI. So I just consider like testing commands and things that are known to work with all the MPI, like MPI CC or MPI run. So no advanced options that are specific to one given family of MPI, like OpenMPI or MPI. Also, this tool is just to test a couple of nodes. I mean, I don't want to, or my goal is not to test the whole cluster, like running benchmark of all pair of nodes, which is really time consuming. So I just want to test the environment, the installed software, which is usually installed on a shared file system, and also not have the same configuration. So basically, testing just a pair of nodes is enough for me. It's a user-oriented testing, so I'm a user, I want to test what I want to do in my environment. So there's no, I don't want to hack my environment to make the test work. I want to fix the installation and the global settings to make this work for every user. And so also my goal is to try to limit what a user will do. So basically, a user will type npicc, execute compiles npi program, npi run to launch its program, and that's it. So the source code is, let's say, it's not very big. It's just so a bunch of scripts. So there are some kind of a few bash scripts, a few ctest, cmake scripts, and also a few lines of R to basically to do the protein. So something interesting, now that I presented this framework, at the end is to, let's say, analyze what happened with all this issue we have with this MPI stack and what kind of problem we made. Most of the time, the problem with the MPI stack are just because of configuration or tuning issue linked to our specific configuration at the University of Luxembourg. So the first one we have is, for example, at the University of Luxembourg, as a job scheduler, we're using OR, which is inspired from PBS, but it's different. And it has a special constraint, is that it's using a special connector. It's not using SSH, but ORSH, which is a kind of wrapper around SSH. So if you want to use an MPI at the University of Luxembourg, actually you have to tell the MPI stack to use this connector. So either you tell your user, you tell all of the users to do this properly, or either you can set the setting in the global configuration file of the MPI. So it will work out of the box. Some configuration you might want to set is tell the MPI to use a proper infinite interface and other things. Some other things, one of the biggest problem we have with MPI is the dynamic libraries issue. So basically an MPI will start a new process on a remote node, and this process, this executable might depend on some dynamic libraries that are not set properly on the remote node. We don't want to hardcode the ALDE library path in the bash chassis of the user or anything, because specifically because of module, you want to switch, you want to change all your AD library paths depending on what you are doing. So there are actually two kinds of problems linked to the dynamic library issue. There is some issue linked to the MPI library itself. Actually, even before the MPI process starts, like the MPI demo from the MPI stack start on the remote node, it cannot even start because its library are not set properly. The other thing could be the dynamic libraries dependency from your MPI program, from the user. Usually, this one are set by the MPI stack itself. But if it's failed to start before, it won't be able to set up the environment for the user properly. Also, we found some bug in some MPI stacks. Like, for example, in Intel MPI version 3, there is some dashism. In the University of Luxembourg, we noticed this bug because we have the dash shell installed as SH. So all these errors are coming out. And also we have some, let's say, you can find some performance issue with some MPI stack. You can consider this as a bug or not, depending on what you think. So now I'm going to make a quick demonstration of the framework. So basically, this is the dashboard where I collect all the results from our testing. So I want to present you the feature of the dashboard itself, which is an open source tool like C-Dash made by the guy from CMake. But what I can show you, we can look at a few tests and see what's wrong and how we can find out. So here on the left column, I have the name of my cluster I tested. Here I have the name of a build. Actually, it's the name of a set of tests. So here I have I'm testing an MPI module which is called iMPI, so Intel MPI 3.2.2. That's it. And so basically here I have the result of the test, so I can see that 5 tests failed, 3 passed, and 5 are not run. Usually they are not run because of previous failing tests. So we can have a look at them. So first we're going to have a look at the Intel MPI stack. So we see basically the one are failing. So for example, so here we see the failing test for this version of Intel MPI. And so when we click on fail, we can see actually the output of the test. And so here we can see this error, MPI error, 63 syntax error. So this test, I have to look at it to understand what happened, but here it is a Bashism in the script, and at the top of the script it's /bin/sh. So basically this test, this error can be fixed just by applying a patch to Intel MPI, changing this bin/sh to bin bash, and that's it. So this could be a patch that could be submitted later to visible guide, so they can have a better version of better installation of Intel MPI. Let's see, one other error we can see here. So here this test is compiling the OSU micro benchmark. So here we see the output of the configure step, and what kind of weird error that we can see is here. GCC 3.9 double quote no such file or directory. So let's say this error is more specific to the software we are building, but for me the bug is inside the MPICC script that Intel MPI is providing. Because if you see the command which is run here, it's, let's say, totally valid command, but a little bit weird because they are escaping the double quote. And I believe inside their script, the Intel MPI script that they provide, they are not doing the escaping correctly, and then at the end this result with this weird error. So this is so this error will happen only with this given software, but for me this is still a bug in the MPI stack that we might want to fix at some point. Let's look at some other details. So here we have, let's pick the latest version of MPitch2. So 3.2.4 compiled with GCC. So here we can see 11 tests. So let's look at the total list of tests. So basically, so here on the left we can see all the tests that are run for this. So basic tests are reach, finding, MPICC, MPI run. Here launching this basic hello world. And we have one test which is running the OSU micro benchmark to measure the bandwidth. So this is the output as a test, and this test runs properly. And there is another test which is checking the result of the latency output. So this the idea here with this test is that we will compare the output of the bandwidth test with some reference file. So we know what kind of performance we can expect on our cluster, and then we're going to compare what we have. So here, on the left, we have our reference bandwidth test that we know that is, let's say, the good performance we expect from our cluster. And on the right, we see the output of this file with MPitch2. And this little symbol on the left of the column tells us that there is a big difference. The difference is like some parameter you can set a level of tolerance. In this case, it's 50%, which is quite huge. So here, this tells us there is a big difference in performance between what we expect. And if we look closer at the result at this number, actually we realize that this version of MPitch, as it is compiled and configured, is not running with InfiniBand, but it's running with the TCP layer. That's a problem. And I think it's good to know that this MPI by default is misconfigured. Also, let's say one of the latest features I added to give a nice thing is to plot the result of the previous test. So in blue is the output that has been run with this given MPI, and in black it is the reference result that we want to have. And the small error bars are actually the tolerance level that we ask for. So if the blue line is between this part, it's okay. If not, that's not okay. And so there is this output for the MPI bandwidth, and there is the same output for the MPI latency. So, yes. How much time do I have? Okay. So we can have another look at a few other ones, which is, let's say, a funny one. Here we can look at NBA Pitch 2, version 1.9. So actually, at the University of Luxembourg, we have one version which is compiled with Ceylon, or two versions with Ceylon, and another one which is compiled with GCC. So this is the same version of NBA Pitch 2. If we look at this one, the performance are okay and in the expected range for the latency, or for the bandwidth and for the latency. But if we look at the version compiled with Ceylon, so the bandwidth is okay, but in the latency we see a big difference. So let's say I haven't investigated myself what's the problem here, but definitely there is a problem. And yes. And so notice that the scale, the Y scale is logarithmic. So it's not, it's a huge difference. It's from 20 microseconds to 200 microseconds. So actually 10 times the latency is 10 times higher in this case. So this is another way to notice like you have some issue with your MPI stack. Yes, what interesting things. So yeah, so you see a lot of red in our in our MPI testing. That's normal. I did a lot of tests trying to push and stress it a bit out. The goal now is, with the help of Fotis, is just to fix all of them and to find what is the right solution for each of the problems. And some of them will end up being some patch and some pull requests sent to the easy build guide for the ones that are not specific to our Luxembourg configuration. Yes. Okay. So some of the future direction of this work. Right now I'm only focusing on MPI stacks. Some other things I would like to test, and which some things that are a bit critical for me, if let's say there are plenty of reasons to fail, is for example the checkpoint restart using the BLCR library. Also testing some other features which are specific to some MPI stack. So using an alternative launcher instead of the before MPI run, some MPI families that provide different launcher. Try to make some run by disabling InfiniBand, but also try to do some checkpoint restart of an MPI job, which is also even more difficult than just checkpoint restart with a single process with BLCR. And also we need some discussion on how to make the detection of the performance issue more variable. Currently we have just a threshold. We have this plot where with a threshold of 50% tolerance, which is a quite high tolerance rate. And yes, that's it. So thank you for your attention. If you have any feedback, any question, comment, some idea of nice features that can be added, you're welcome.
Right, you have time for one question? Are there any other sites that use this? Are there any other sites where they use this? Other than yourself?
Only ourselves. So it's just a prototype and just building it up.